Okay, so we are planning to cover section 2.5, infinite limits. This is the section. There are two objectives in this section. We would like to determine infinite limits from the left side and from the right side. As usual, whenever we talk about the limits, we also have to make sure that it's from left and right. And then eventually, using this infinite limits, we can also use the very same idea to find the vertical asymptotes to plot the graph of a function. Let's start with one example. Let's say you have a function f of x which is 3 over x minus 2. So if you try to plot the graph of this function at x equal to 2, this is actually 3 over x minus 2. So when x is 2, this denominator would be 0. So 2, it's 0 here. So that means the function is undefined at 2. But if you go to the right side of the 2, the graph you would see would be look like this. Okay, let's say x equal 3, then that is 1, and then so on so on. If you go to the left of the graph, then you are going to find the graph look like this. So what is happening here, when x approaches to 2 from the right side, the function is going up and there is no bound for that. When x is approaching to 2 from the left side, this negative sign means from this direction, the function is going down. So going down, where it's going, if you see this arrow sign, it means there is no stop, there is no bound. So that means when x approaches to 2 from the right side, the function f of x is approaching towards positive infinity. This is the symbol we use because there is no bound. That's why we use this infinite symbol. Similarly here, when x approaches to 2 from the left side, the function is decreasing. It's approaching towards negative infinity, meaning it's going down. So they are called, infinite limits. So one more time, this is the graph. F of x increases and decreases without bound when x approaches to 2. From the right side, it's approach to infinity, and from the left side, it's approach to negative infinity. So this is the concept. This is the notation we use for infinite limits. If the function decreases without bound as x approaches to 2, in this case it's a 2, or maybe it could be any value from the left side and from the right side, that's called infinite limits. We can also verify this thing by using some table. As you can see here in this table, if I pick value to the left of the 2, as I approach towards 2, the value of the function is keep getting down and down, keep getting decreasing. Yes? And if I pick the number from the right side of the 2, as I approach to 2, the value is keep growing and growing. There is no bound for that. So as you can see here, the function is increasing without bound if you go towards 2 from the right side, and the function is decreasing without bound if you approach the 2 from the left side. Okay, so these are the things we're going to write: negative infinity and positive infinity. A limit in which function increases or decreases without bound as x approaches a value c is called infinite limit. This is a proper definition for the infinite limit. Let f be a function that is defined at every real number in some open interval. So in this case, the function is defined at every real number in some open interval from negative infinity up to c, and from c to positive infinity. The statement, the limit of the function f of x when x approaches to c is infinity, this is a positive infinity, means that for any real number, positive real number m, look at here, you can pick this m higher and higher. This m could be 100, could be 1000, could be million, could be trillion. It doesn't matter. If the limit is infinite, you should be able to find the delta, meaning you should be able to find something around this c such that the value of the function in that open interval would be positive infinity, would be greater than m. Okay, that's the proper way to define the limits, infinite limit. And if in opposite situation, similarly, you could have the negative infinity if the function is always less than some any real number, negative real number n. Okay, so if we are talking about the limits, infinite limit from the left, then we always keep x from this left side. Look at here. Here is the c, and you are trying to create an open interval around c. This is positive delta, this is negative delta. So if you pick anything from this left side, let's say x from here, which is actually x is greater than c minus delta and then less than c. This is c minus delta and this is c plus delta, sorry, because we're talking about the delta distance here. So that's called infinite limit from the left. Similarly, if you pick your x value from the right side, that's called infinite limit from the right. One example here, let's take one example function f of x, which is negative 1 over x minus 1. When x approaches to 1, as you can see here, from the right side, the function is going down, it's decreasing. That's why the function approaches to negative infinity if x approaches to 1 from the right side. Similarly, when x approaches to 1 from the left side, the function is going up, it's increasing. So the function is going to the positive infinity as x approaches to 1 from the left side. So in this example, you can say that these are the infinite limits. Okay, so positive infinity and negative infinity, these are the two infinite limits based on the situation we have given here in this example. So now, how we can use this concept of infinite limits for finding the vertical asymptotes? So there is a definition of vertical asymptote. If function f of x approaches infinity or negative infinity as x approaches c from the right or left, then the line x equal to c is a vertical asymptote of the graph of f. So whenever you find the infinite limits, you can also find the vertical asymptote at the same time. When the limit of the function when x approaches to c is positive infinity or negative infinity, this value gives you vertical asymptotes. So there is one theorem which says, let's say you have a rational function f of x over g of x. To find the vertical asymptote, just equate this function in the denominator with 0 and solve for x. That will give you the vertical asymptotes if there is any vertical asymptotes. For example, let's say you have a function x squared plus 1 over x squared minus 1. To find the vertical asymptote, always find factors on the top and factors on the bottom. In this case, the top function is unfactorable. So this is, you cannot factor, this is the prime factor. But on the bottom part, you can factor this x squared minus 1 as x minus 1 and x plus 1. So as you can see here, when x approaches to 1 or negative 1, this denominator gets 0. That means this function gets infinity. It might be positive infinity or negative infinity. In any case, x equal to 1 and x equal to negative 1, they are vertical asymptote. So look at the graph of this function here. When x approaches to positive 1, from the right side, the graph is approaching towards infinity. And from the left side, the graph is approaching towards negative infinity. Similarly, when x approaches to negative 1 from the right side, the graph is approaching to the negative infinity. And then when x is approaching to the negative 1 from the left side, the graph is approaching to the positive infinity. Okay, so that's how we can find the vertical asymptote. And in graphing technique, we can use the vertical asymptote to plot the graph. More about the graphing we're going to discuss later, in one of the section in this course. Okay, some properties of limits. This time properties of infinite limits. So let's say you have a function with the infinite limit, and there is another function with a finite limit. So then you can find the limits of some of these two functions. It would be infinity, because infinity plus L, any finite number, is infinity. If you try to find the difference, that would be itself infinity. If you try to find the product, depending on what L value you have, if this L is positive, the the limit of product of these two functions would be positive infinity. But if this L is negative, the limit of the product of these two functions is negative infinity. Keep in mind, we're talking about this limit when x is approaching towards the same number c. Okay, and again, for the quotient, if you try to find the limit of the quotient g of x over f of x, then that would be 0. So the very similar property we can also apply for one-sided limits. Example, we know that the limit of 1 when x approaches to 0 is 1. Limit of x squared when x approaches to 0 is infinity. And now we can combine these two, and we can find the limit of 1 plus 1 over x squared, because limit of 1 is finite and the limit of this is infinite. By using the first property of the sum, that would be positive infinity. So now you can apply the very similar type of these properties for these problems. Okay, so that's infinite limits.